Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you can refer to my GitHub page at this given link. In this lecture, I will be discussing linear discriminant analysis for feature dimensionality reduction. In last few lectures, we have seen that PCA finds the direction that are efficient for data representation. However, in this lecture we will talk about the discriminant analysis that seeks direction that are good for discrimination or separation between features from different classes. Now look at this plot. So here we have two plots. So we have the same set of samples on both the plots, where black dots are from class 1 and red dots from class 2. However, their projection are onto two different lines. So these are basically the two different lines in these two plots. The left hand side plot shows the direction of line passing through the origin obtained using PCA. So this direction we obtained using PCA, and if we project the data on this line, then that will be best projection of data in one dimensional feature space. On the other hand, the right hand side plot shows the direction of line passing through the origin. So if we project our data points on this line, then separability of the data points will be maximum in some sense in one dimensional feature space. So here this portion is for class 1 and this portion is for class 2. So here we will have the set of samples. So here we have set of samples which is from class 1, and these are the set of samples which is from class 2. So now just to think on it, that what we should do, that these two that means these two projected samples should have good data separability. That means the mean of this class should be well separated from the mean of this class, and the variance of this class should be minimum and variance of this class should be minimum. So these two criteria should be fulfilled to obtain the good separability of the data in this projection. The linear discriminant analysis find the direction of this line, so that the mean of these two class will be maximum and the variance of these two class will be minimum. Now let us suppose we have n number of data samples in d dimensional feature space, and that data samples are divided into two subsets d1 and d2 corresponding to the class omega 1 and omega 2 respectively, and n1 is the number of samples in subset d1 and n2 is the number of samples in subset d2. So here in linear discriminant analysis, our goal is to find the projection onto a line defined as y equal to w transpose x, such that the points corresponding to set d1 and d2 are well separated. So that is basically our objective. So when you will look at this plot, so this is the direction that we are looking for, where the set d1 and d2 will be well separated. So on this line we will project all the data points. So these data points will be projected on this line. So in this way we can project all the data points. So let me draw the points. Here we have to find the best separability in the direction of w. Okay. Then what should be the criteria? Definitely the mean of these set of samples from class 1 and mean of the samples from class 2 should be well separated, and within class variance should be minimum. That should be the criteria to obtain such separability. When we will project all the data samples on this line, then we will have the set of n samples, that is y1, y2, yn, and that will divide into the subset y1 and y2. So now we can define our criteria function for best separation, which can be defined as using this expression, where mi is the sample mean and si square is the scatter of the projected samples from the ith class. So if you will notice here that numerator part is basically the difference between the means of the projected samples, and the denominator is the sum of the scatter of the projected samples for different class. We can analyze these parameters where the sample mean is given by using this expression, and the scatter of the projected sample is given by using this expression. Now try to analyze these parameters. So we can write the projected sample mean mi tilde as so it will take the summation of all the projected samples from set yi, and we know that y is basically the w transpose x, then our mi tilde will become so here we have sample x, so our set will be changed. So now x is all the samples from set di. So now we can write w transpose into 1 by ni and rest of the term. So this is basically m I. So now we have mi tilde is basically the w transpose mi. Now we can compute m1 tilde minus m2 tilde equal to w transpose m1 minus w transpose m2 equal to w transpose m1 minus m2. Okay. Now we have to compute m1 tilde minus m2 tilde, and this was the numerator term of the criteria function. Okay. So basically this term is denoted as WB, which is called between class scatter matrix. Okay. Now look at the scatter of the ith class, which is denoted as si tilde square, and which is given as so y will be W transpose X and Mi tilde will be W transpose Mi. So we have to take the square of this term, and here X will be the samples belongs to the set Di. So now we can simplify it. Okay. So now what the value we obtained, Si tilde square equal to W transpose X minus Mi X minus Mi transpose W, where X is the samples from set Di. Okay. So now we can write W transpose, because W is independent of X, so we can write like this. And if you remember, this is the term which is called the scatter matrix. So now we can write W transpose Si W. So Si square is basically the W transpose Si W, where Si is summation over X minus Mi X minus Mi transpose. So now we would like to compute S1 tilde square plus S2 tilde square, which is the denominator of the criteria function. So W transpose S1 W plus W transpose S2 W. So this is basically the linear relation. So we can write W transpose S1 plus S2 into W, where the S1 is the scatter matrix of the samples in set D1, and S2 is the scatter matrix of the samples in set D2. So now we can write W transpose SW, where SW is basically the S1 plus S2, which is called within class scatter matrix. So here we obtained the two terms. First is SB, which is the between class scatter matrix, and which was M1 minus M2 into m1 minus m2 transpose, and the another term we obtained, the scatter matrix, which is S1 plus S2. Okay, here m1 minus m2 square is W transpose SBW and S1 square, S1 tilde square plus S2 tilde square is W transpose SW W, where SB is the between class scatter matrix, where SW is within class scatter matrix. Then our criteria function will become like this. Just we are putting the value of numerator and denominator that we just derived. So this is our final criteria function. So this criteria function is basically a well known mathematical physics as the generalized Rayleigh quotient. So now we have to maximize this criteria function with respect to W. So a vector W that maximizes the criteria function must satisfy this expression, and if we multiply both sides using SW inverse, then we will obtain this expression. So if we analyze this equation, that we can see, observe that, so this is our matrix SW inverse SB, and W is eigenvector and lambda is the eigenvalue of this matrix. But in this particular case, we need not to solve this eigenvalue problem, because the SBW is always in the direction of M1 minus M2. So we can directly use the solution as W equal to SW inverse into M1 minus M2, where M1 is the mean of the samples from class 1, that is the set 1, and M2 is the mean of the samples from class 2. So this is the weight vector that we are trying to find. So this is our final solution. So this is the direction that we were looking for. So few things we can note down here, that SW is symmetric and positive definite, and it is usually non-singular if the number of samples is greater than the dimensionality of the feature vector, and SB is also symmetric and positive definite, but its rank is at most 1. Thus we have obtained W for Fisher linear discriminant function. So what is Fisher linear discriminant function? It is a linear function which gives the maximum ratio between class scatter to within class scatter. If you have any doubt, you can ask in the comment section. Thank you.